Hello guys. So for uh, for a week I am not able to live stream due to lack of good internet connectivity. So I'll be just uploading the videos. So yesterday we have solved the problem kth smallest element in a BST. Okay. So let's see what approach we have used. So this is the kth smallest. So yesterday, 21 hour ago, we had a submission. So what we did was we basically did a in order transversal of the tree, and as we know, the in order transversal of a binary search tree gives a sorted list. So we have stored the element of the binary search tree into this list, and we have returned the element at k minus 1th index. So that was our kth smallest index. So here this takes big of n time complexity and big of n space. So let me paste this solution here. So what we can do here is, as we know, we only need to return kth element. Okay. So instead of adding it to the list, we can have a count variable which can count that how many numbers I have added to my list, and when I reach the kth element, I can simply return that element. So what I can do here is I can make an answer variable, initially set it to -1, and a count variable, set it to 0. Okay. So instead of list, I will return answer at the end. And instead of adding to the list, what I can do is I will increase my counter that I have found a element, and I will check if my count becomes equal to k. Okay, so we also need to find pass the k in these calls also. Then we can set our answer to root dot value. Okay, so basically this is the most optimized approach. Its time complexity is big of n, and its space complexity is big of 1, which is constant time complexity. Okay, so we also do have a follow-up here. So the follow-up says if the BST is modified often, we can do insert and delete operations, and you need to find kth smallest element frequently. How would you optimize? So for this follow-up, I have found a approach in the solution section. In that approach, what was mentioned there, that we should do a change in our tree node structure. We can have an extra column, extra value which says the count. So basically in this count, what we will store the number of element present under that node. For example, for 3, that count would be 3 because 3 has 3 element attached under it. For 1, the count will be 1. because one have one element under it. So I think that's how we can say that we can find our kth element. Means we can go from left part, and we can check how many element are under one on the left side. So on the left side of one there are zero element. On the right side there is one element. So the number of element on the right side plus this node will return our answer. For example, here number of element on the left side are 2, and adding plus 1 gives us k is equals to 3. So that's why 3 will be our answer here. Suppose we need to return suppose our k is 6. So in that case, so number of element on the left of the 5 are 4, and number of so we can say that the number of element on the left side of the 5 plus the 5 itself, which is 5, are smaller than k is equal to 6, so smaller than 6. So in that case we can move to right, and we need to find 6 minus 1, 6 minus 5, 1, one element on the uh, right side of the 5. Okay, so I think what we need to store here is we need to store number of element on the left side in the count variable. So I can also show you that solution. So this was the solution I'm looking at. So here what Henry is doing, basically he has created a new tree, root with count. So how he found this approach? So basically in description itself, in the hints, we are given a hint. What if you could modify the BST node structure? The optimal runtime complexity is big of height of BST. So I think this was the solution. What if you could modify the BST's node structure? It's not okay. So what the Henry is doing? So he has created a new tree with count variable. So here is the definition. He has added a count variable here and initialized that count to 1. So created a root node with value, so its count initialized with 1. Then uh, he moved on the left side and then on the right side. So after that call, we will check if left side is not null, then we will add the number of node on the left side to the current node, and also the number of nodes from the right side to the current node. Okay, so here he is storing total number of nodes under a given node. Total number of a children node present, including the current node. Okay, and then uh, we are returning. He is returning kth smallest element using this approach. So in this approach, first uh, he moves to the left part, assuming that our answer will be present on the left side. Suppose in this example, if we had some node attached, suppose this 7 6 was 6 is 7. Okay, so we have a BST. So is he using the property of BST somewhere? I think he's not using property of BST anywhere. Okay, so we will go on to the left part and check if number of node on the left is greater than or equal to k. Then in that case we can move to the right part. Or if the number of left node are k minus 1, then we can return current node's value. If the nodes are smaller, then we will move to the right and we will decrease this number of nodes. Sorry, this number of nodes from the k, because we have removed these number of the nodes from the left side. And in else part, when our left part becomes null, we are moving to the right part. And while moving to the right part, we are checking if k equals to 1. Suppose in this example, after moving to the right, what we will do, we will decrement this part from the 6. We are taking case where k can be 6. So we reach this condition and then we check our k is 1. Yes, our k is 1. Then in that case, we will return 6. Otherwise, we are again calling our function for k minus 1, this same function for this part. Okay, so I think this is a good approach if mode for the follow-up, but without follow-up, this basic approach is sufficient. So these complexities are best. And if modification is required, I think this approach is good. Okay, so we will be revisiting this problem. So I have also marked, we have marked this problem as favorite. So can we see that how many problems we have in favorite? Okay, I don't think there's list which shows favorite. Okay, so Next question we will solve is construct binary tree from pre-order and in-order transversal. Okay, so I have opened this question here. So given two integer array pre-order in-order, where pre-order is the pre-order transversal of a binary tree and in-order is a in-order transversal of the same tree. Construct and return the binary tree. Okay. So for example, for this particular tree, we are given the we have pre-order transversal and in-order transversal, and we need to construct that tree. Means we need to construct this tree and need to return tree dot node. So in pre-order transversal, basically we first visit root. After that root, then we visit left part. Then we visit right part. So this is our pre-order transversal. Let's copy this pre-order transversal. Okay. Then in order transversal, we first visit left part. Then we visit root. Then we visit right part. So let's see this example. So basically for this particular tree, this is my root part, okay, and this 9 is my left part, and this rest of the part is right part, considering 3 as the root, okay. And for in order transversal, this 9 is my left part, this 3 is my root part, and this is my right part. So this is how we can divide these parts. Okay. And we need to construct this tree. So one thing like we can say is this is the root of our tree. Means first element of the pre-order transversal is root of the our tree. So suppose okay, this is the root of the our tree, and we will suppose we find this root here. So one thing we can say is this is our left part and this will be our right part. Okay. So how many elements are present on my left part? How I can decide is that how many element on the left side of the in order transversal are present on the left of the 3. So basically here one element is present on the left of the 3. So uh, starting from this root node, the one element will be present in the root of the in the left part of the tree, and else will be present in the right part. So that is how we can divide our uh, this array in the code. We can check the position of these three, and the same positions index we can find in order, and this index will divide the left part and the right part, and similarly we can divide this part. Okay, so we can then surely uh, say that this part which is present on the left of the three in the in order transversal will be a part of the left left tree. Hmm. Let's say I initialize a function utility function which takes a pre-order and in-order transversal. Initially, suppose we pass 0, that this whole tree is a taking considering this whole tree, and pass the in-order transversals dot length. Okay, so public util this is the starting index and this is the ending index. Okay, so for this array, what will be my root? So the element present in pre-order at 0th index will be my root. Okay, so I initialize my root. Root as a new tree node. Okay, new tree node. um, Pre-order. Okay, S. And at the end, I will return this root node. Okay, so now I need to construct a left part of this tree using the same function, and right part of this tree using the same function. Now I need to decide that on the left part, uh, how much array means how much portion of the pre-order will be a part of my left tree. So as we discussed, we can decide it using the position of 3 in order transversal, and number of element on the left of the 3 uh, will be a part of the left subtree. So suppose we need to find the position of 3. Okay, so as mentioned in question, the values can be unique. So we can uh, make a hash map to store the indexes of the, let's say, in order transversals. So instead of let's just have a map of integer and integer, new hash map, Let's call this position in order. So for int I equals to 0, I less than, let's define length of these arrays. Okay, so in position map we will be putting the value in order at ith position and its index. Okay, so the position of this uh, element s element in order will be, so I think we can pass map instead of this in order. So okay, so now we have map. Okay, so position will be map dot position map dot get pre-order for the safe side we can use get or default pre-order s. So now we have position, so position of these three. So now we need to decide that how many elements on the left side are present. One thing I have to do is the my left part in the pre-order will start from s plus 1 for sure. This is s plus 1 and number of node on the left part. How can I decide number of node on the left part? And this right part will end at e position. I'm also sure about this. Now I need to decide this left part's starting position. Sorry, ending position. Okay, let's think. Okay. So I have thought of an idea. So how we will so we are at this position. We have found this position. Now we need this left part. The number of nodes in this left part. So number of node in this part will be position of this node and minus its node. I think we also need to track position in this array also. Suppose I call that index. Initially I am at this node. Let's call this index. Okay, I am at 0th index initially, and instead of taking this, let's take okay. So we have found this position. Now as our s remains same and our position, this part becomes s minus 1 and this part become position plus 1. Okay, so now we need to decide what index we will pass from here. Okay, so the for the left part we will be passing index plus 1, and for the right part we need to pass this index. So how we will find this index? So as we have calculated a number of element on the left of the root, so that will be idx plus number of element on the left of the root. So that would be position minus, suppose here position is 1, and this index will be a starting index. So here so idx is 0. Okay, so position is position is 1 1 minus 0 1, so idx plus 1, so I think we also need to add a 1 here. So if our s becomes smaller than e, in that case we can return null. Let's try running this. Okay, we are not getting any output. Sorry, if s is greater than. Okay, we are getting index out of bound. Let's see. Okay, let's try submitting this. Okay, we have got a submission. I didn't expected. So basically here S and E are the part of the in-order transversal and index is the part of this. So let's see my previous approach. So what I did here is I have found the what I have found here. I'm confused what's index here. Okay, index is 0. So basically this is the index in pre-order. Okay, so I'm looking for index. If I have found index, okay, element at index position in pre-order, then I am breaking and increasing my index and that making my left part as this s minus j and right part as this. Okay, so I think the approach we have used now is a bit good because we are doing this operation in constant time. We have stored the positions and we also don't need a global variable in our new approach. Okay, we have done this problem. I am constructing the left part first. Okay. Let's see some solutions. Okay. I think everyone is using similar approach. Okay, so I think that is it for today.